I've never really felt like I understood the solution to the twin paradox intuitively. Just to recap, the paradox goes something like this. A spaceship leaves Earth and travels to a distant planet at a considerable fraction of the speed of light. Then the rocket turns around and heads back to Earth. Surprisingly, the amount of time elapsed for the rocket is less than on Earth. Intuitively, you might argue that during the trip, the same amount of time should pass on Earth and for the rocket, since from the rocket's perspective, Earth and the whole universe is the one moving. Let's look at the journey from Earth's perspective, which we'll take as an inertial frame of reference. The space-time diagram shows the paths of the objects, with distances on the horizontal axis and time on the vertical axis. Let's say that the rocket leaves at 80% of the speed of light and travels to a distant planet 5 light years away. The one-way trip takes 6 years and 3 months, so the total time elapsed on Earth is 12.5 years. For the rocket, we can calculate that the effective time dilation reduced the journey to only 7.5 years, which is considerably less. To gain some intuition for what the rocket might experience, let's look at the co-moving frame. We'll boost into the frame that's moving together with the rocket at each instant along the rocket's path. As soon as the rocket reaches traveling speed, we observe that the distance to the exoplanet shrinks to 3 light years. This is length contraction in action. We can also see that each year on the planets no longer corresponds to 1 year in our frame, but to 1 year and 8 months. This is the result of time dilation. Next we see Earth moving away from us as the other planet approaches. We complete half of the trip after 3 years and 9 months, while only 2 years and 3 months have passed on Earth. So again, less time passed in the moving frame, and the paradox seems to hold. If we double the time to get the total span of the journey, we would incorrectly conclude that from the rocket's point of view, less time passed on Earth in total. And then we turn around. This is where the symmetry breaks. The time on Earth skips forward a whopping 8 years, while we essentially stand still. It's not that the acceleration is 0, but we take the amount of time we spend accelerating to be negligible in this specific case. Of course, the only way we can change frames like this is by accelerating, but the effect really depends on the total change in velocity and the distance between the objects. The further away, the larger the effect. The trip home again takes 3 years and 9 months. Back home we compare our clocks and get the exact same result we observed from Earth's frame. 7.5 years passed for us and 12.5 years passed on Earth. Finally, we are ready to look at the proper frame of the rocket. In this frame, we can see that the world lines are either discontinuous or have missing events. No boosting is involved, this transform is not Lorentzian anymore. A linear transformation can't create the kind of discontinuities or jumps that we observe. Everything looks similar to Earth's frame except for the distances involved, and notice how the exoplanet jumps towards us as we speed up. When we turn back, we observe yet again that Earth's proper time skips forward 8 years instantaneously. In the end, we get the exact same results. Looking at the paradox from these 3 different perspectives really helped me gain a lot more intuition for how special relativity works. But there's still so much to learn. As an exercise, draw the rocket's frame and try adding labels for the time passed on the exoplanet.